Hello, let's do some more limits. Okay, so in this one, now we get to go into limits of trig and exponential functions in an analytical approach. So we're going to look at this, we're going to do some algebra, we're going to rewrite this. It's going to be awesome. Get excited. Okay, so what we want to try first on any of these is just to try to substitute if we can. So let's do that. So in this first one, if I say sine of 3 times 2 pi over 3 divided by 3 times 2 pi over 3. So what I want to find is the sine of 2 pi. When I do that, remember I think of the sine curve, but you can do this another way, that the sine of 2 pi is 0 over 2 pi. 0 divided by anything is 0. Easy peasy lemon squeezy. And you thought this was going to be difficult. Okay, in the next one, I'm just going to rewrite this first because I think sometimes people have trouble just putting this in your head when it's written like this. So I'm going to say cosine of theta, and then you square it. So you substitute in first, and then you square. So, oh, this was a 2. It looked like pi squared. I couldn't read my own writing. Anyway, I'm going to say this is 2 cosine of pi, and then I'm squaring it. So cosine of pi, in my head, this is how I do it, but you can decide how you do this. This is 0 to 2 pi, so at pi, this would be -1. If I square it, -1 squared would be 1 times 2. Now I get 2. We did it. Okay, moving right along. I'm substituting in 3, just if I can. So this would be e 2 minus 3 plus 2, which is the same thing as e to the negative first plus 2. And anytime I have a negative exponent, I would just say rewrite it as 1 over e, and then you can put to the first. You don't have to put the first in here, plus 2. Just because I see people, if you actually have to make or go further with this or evaluate in some way, like actually do something with this answer, lots of people struggle to get it from here to here. So just do it every time so you don't forget that a negative exponent just means that, oh, this would just transfer the bottom to the denominator with the same exponent but positive. Okay, so just because something looks scary doesn't mean that it necessarily will be scary. It's just try substitution first. There are some times when that won't work. So just because you substitute in, so like in this one, and I get 1 minus cosine of 0, sine of 0, and then I square it. This would be 1 minus, remember cosine of 0 would be like, I can't see that, sorry. Cosine of 0, this was my cosine, would be 1. Sine of 0 is 0. If I square that, I would get 0 over 0. This doesn't work. That doesn't mean the limit doesn't exist. So do you see how I didn't put the equal sign in between them? Still not. Okay, so in this one, this function is undefined, but what could be happening is there could be a hole in the graph, and if there's a hole, that the limit could still exist, because for a limit to exist, what has to be true? That's what you're supposed to say. You're not just supposed to look at me going like this. Okay, the left-hand limit has to equal the right-hand limit. So the limit from the left equals the limit from the right. So let's try this one and see if there's something else we can do. There's actually a couple different ways that we could do this, depending on how you think of it, but I'm going to think of it like this. So in pre-calculus, you probably did this depending on the time of the year, and you may or may not remember it, but there are some trig identities. So trig identities where you can change one thing into another, and most of them we don't use in calculus. Some of them, if you go to BC calculus, you would use there, but in AB, not so much. So one of the things that the trig identity that you actually like need to know in calculus is this one. It's called the Pythagorean identity. And it's just sine squared plus cosine squared is equal to 1. And it's of theta, of course, because you can't have sine squared or cosine squared without an angle. So this is equal to 1, which means sine squared would actually be equal to 1 minus cosine squared of theta, if I subtract cosine squared on both sides. So I'm going to rewrite this. Limit as theta approaches 0. The numerator is 1 minus cosine of theta. The denominator is 1 minus cosine squared of theta. And so the reason why I'm saying this, and we're doing all this work and rewriting it, because this doesn't look good either, and it's not like we can start crossing things out. Remember, if you divide and you're like 1 divided by 1, and you got, and you're like, it cancels out, 1 of the cosine, 1 over cosine, and you just got that, somewhere there's a dead bunny. And I'm really sorry that you're responsible for that. So don't do that. What I want to do instead is I can factor this. Limit is theta approaches 0. The numerator is 1 minus cosine. Cosine squared is a perfect square. 1 is a perfect square. This is the difference of perfect squares. So 1 minus cosine of theta times 1 plus cosine of theta. If you need to stop and look at that and see like and actually multiply this out to agree with me, do that. That's the beauty of video. Okay, so in the numerator and denominator, you see how now I have 2 of the same things, and this is the numerators all together. The denominator is a product of terms where I've got this times this. So that goes away. And I know that there's a hole wherever 1 minus cosine of theta is equal to 0. In this case, that's at 0. So I would have 1 over 1 plus cosine of theta, which now I can substitute in, and I can say 1 plus cosine of 0. If I think about what a cosine curve looks like, cosine of 0 is just 1. Ta-da! The limit exists, and the left equals the right. Very exciting. Okay, so that's the first part of this. Let's do another one. So if I want to try this, I'm like, okay, I'm feeling good. I'm seeing that there are trig functions and I can see the limits. And so what can I do? So the first thing, if you want to substitute it in, you can do that. If you're like, I don't know what the tangent is of 3 pi over d, and I don't want to do that yet, but I do know that tangent can be rewritten. You're always allowed to do that too, if it just makes life easier for you. So when I see tangent, another thing, that tangent is in one of the identities that I'm hoping that you remember too. I just said you only have to remember 1, but you also have to remember for tangent and secant and cosecant. But I believe in you. You got this. And contact me if you're like, I don't know this at all. And then I can make a different video on that or point you in a direction where you can learn this. And then you're like, oh, I'm a boss. Okay, so tangent is actually just sine of theta divided by cosine of theta times cosine of theta. Oh my goodness, this problem. It's too easy. We got this. So this problem is just the limit is theta approaches 3 pi over 2 of 3 sine of theta, and then substitute. So you'd have 3 sine of 3 pi over 2. If I think about a sine curve, looks like that. This would be 0, 2 pi. This is pi, 2 pi. This would be between 0 and pi would be pi over 2, or half of a pi. Over here would be 3 pi over 2. That's the part that I'm talking about. Oh, -1. Yes, there are other ways to do this. If you're remembering the unit circle, good for you. Do it. I don't care how you do it, as long as you've got it correct and it's not like some made-up way. Okay, so for secant, I want to think about this and think, okay, secant, I remember that's something with either sine or cosine or whatever. Secant is 1 over cosine of theta times cosine of theta. Oh my goodness, this is so nice. Cosine cancels out. That means there could be a hole in the graph, but it also means that I just have limit is theta approaches pi over 2, 1 over 4 times theta. Are you sad? Because you're not even doing any trig. You're just substituting in. 4 times pi over 2. 4 divided by 2 is 2. Woo! We did it! Okay, let's do another one. Limit is theta approaches pi. You should be trying this too. So pause at any point. You try it. Cosine of theta. Tangent is just sine over cosine. Then I've got over sine. Cosine and cosine cancel out. But then look at that. Got sine of theta over sine of theta. That goes away too. Like, what am I left with? That would be the same as limit as theta approaches pi of 1. which is just if any constant, we would get 1. Woo woo! We did it. Okay, move them right along. And this one, so it's important to note that as in all cases of evaluating limits, direct substitution should always be tried first. So just like we did above, but sometimes it won't work. If that does not yield a value, then simplification of the function can be tried. So what that means is we can try factoring, we can try all the things that we did above just to see if we can do something else with it. There are some cases where even that doesn't work. There's a crazy function, and this is what it is. So what I want you to do, using your graphing calculator, complete this table. So see if you can do that on your own. I'm going to fill in the values in a second, but I'm going to go to y equals, and sine of theta over theta, I'm just going to write as sine of x over x, same thing. And I'm going to change my window because for sine functions, I'm only going to go from like 0 to 2 pi. And not negative 10 to 10, maybe negative 2 to 2 instead. And actually, I want to see 0 here, so I'm going to change my window so that my x-min is like negative 2 pi. Okay, so I can see what's going on here. And I see a sine curve of some sort. It looks kind of different because this is sine of theta divided by theta, so it looks different, but it's still like the wavy kind of function we know and come to love. No? Maybe not? Okay, so what I want you to see though is if I try putting in all these values, so you can use second, calculate value at negative 0.01, and I'll get 0.999. And I could keep going if I wanted to. Try doing that for all the other ones. Second, calculate value, and then find all these. But I'm going to keep going. This one actually is entirely close to 1 and 1. And I could even do more than this. Like this one's actually 0.9999833. There you go. That looks kind of weird, but the decimals just keep going on. So these aren't exactly the same, but you can see these are all the values really, really, really close to 0. So if I think about approaching 0 from the left, this value, in fact, when I put in 0.000001, my calculator rounds it to 1. Actually, it doesn't. It does, if I do value at negative 0.0001, I get this, where it says x is negative 1 times e to the negative 4th. What that means is negative 1 times 10 to the negative 4th, meaning super close to 0, I get 1. Super, super close, I get 1. So this is written just in scientific notation. I get 1. Even though it's not exactly 1, our calculator is rounding to that place. So from the left, I get 1. From the right, same deal, I get 1. So the limit as x approaches 0, or theta approaches 0 in this case, would have to be 1 because the left equals the right. And that's what I know by the limit existence theorem. The problem is, if I say second, calculate value at 0, it doesn't exist because you can't divide by 0. But we know this to be true. Okay, so go a little bit further. There's something we can do with that. If I do the same thing, but now instead of sine of x, I say 3x divided by 3x, and don't write it like this. There's a problem. What your calculator do would be dividing it by 3, but not 3x. So I'm going to push insert to move it over. You have to make sure that your parentheses are around the denominator. And if you're like, why isn't it around the numerator? This is actually not multiplied. It's one single function. But if you want to make sure that you're good, you can always do that. Oh, sorry. So I'm going to insert. You can always do that. Be sure that you've got everything in the numerator in parentheses and everything in the denominator. Okay, so if I graph this, oh my goodness, it's like the same thing. What is happening here? Okay, so if I'm doing second, calculate, and I'm going to do the value, negative 0.01, I get 0.9998. 5, and then I can keep going. You can do all the other values also. I wonder if I have this one that is easy that I can just copy it over. There it is. Found it. Okay. So in the next one, it's still 0.999. There's actually 5 nines this time. So it keeps getting closer and closer and closer. This one's like ridiculously close. 6, 7, 8, and then that goes to 8. So this one is essentially like 0.9991. It might as well be 1 if I'm going left and right. I'm just writing this and I'm truncating it, so not rounding to go to 1. Whew, I threw this. I'm not angry. Okay, here, same thing, 0.9985. Yeah, so a lot of 0.99s. We know we're going to this value. If I'm going left or right, I can see that I'm approaching this value of 1. This looks super similar to the other one. Left and the right are equal. Anytime you see something like this, so this is something you're going to want to have in your head, memorize it, so that you can use this when solving other limits if you see they look like this. Anytime you have sine of c theta times, or divided by c theta, anytime you have that, you get 1 when c is any constant. So we're going to be able to use that in a little bit. Okay, now in a similar fashion, if you use your graphing calculator on this one, and we complete this table, something similar occurs. So if I say in the numerator, make sure that you definitely put parentheses, 1 minus cosine of x divided by x. When I graph it, you could have put x in parentheses, but it wouldn't have actually mattered because it's the only thing in the denominator. If I checked out all these values, I can see there's a smooth curve happening. Second, calculate the value at negative 0.01. And I get negative 0.005. I do the same thing, but I do the value this time at negative 0.001. And then this one says 5 times, or negative 5 times 10 to the negative 4th, which is essentially 0. So if this was rounded, if I put this in the other part of my calculator, like in the home screen, I get 0, 0, 0, and then there's like 4, 9 here. But it's rounding it to 0 here. Like that's how close that we're getting. And the next one, same thing. If I were on the home screen, I could do this. 3, 4, 5. So if you don't believe me, keep trying this, or if you're having a tough time putting it in your calculator, try that. Sorry, I'm not being consistent at all. Some things I'm rounding, some of them I'm truncating, whatever. Doesn't actually matter. What I care is from the left and from the right, I'm approaching the same value, which in this case is 0. So the left equals the right, I get 0. So the other thing that you have to remember then is this one. So you remember this and this. So if you want to star something on a page, those are the 2 things to star because you need to remember them in some way. Oops, sorry, there it is. Okay, I'm gonna pick up and practice in the next video. So thanks, bye.